So I'll just start. So hello, everybody, and welcome to Frontiers in Physics webinar in Quantum Engineering and Technology. So this is the second Quantum Engineering and Technology webinar for our journal. And we're very excited to have you join us in this discussion centered around basic methodologies in quantum physics to support the quantum engineering community. My name is Nila, and I'm a content specialist at Frontiers in Physics. And I'm joined here today by my journal manager, Ilaria Prete, and our two associate editors, Dr. Marcus César de Oliveira and Dr. Omar Magaña-Loaiza. So to give you a quick outline of today's program, we will first introduce our two speakers for today, our associate editors, Marcus and Omar. And first, Omar will start by telling us about multiphoton quantum technologies, and then we will move to Marcus's talk about the impact and perspectives of quantum technologies 2.0 in short and medium term. And lastly, we will have a discussion where you will be able to ask your questions to both of our speakers. So please put your questions in the Q&A and we will address them during our discussion in the end. We are very thankful for all of our speakers to have accepted to join us in this webinar. Omar is based at Louisiana State University in the US as an assistant professor, and Marcus is a professor at the State University of Campinas in Brazil. And I will now hand over to Omar, who will tell us about multiphoton quantum technologies.
Great, thank you. Thanks for the introduction. I will share my screen. Share. There you go. Well, thanks for the introduction. As Nele said, my goal is to tell you or to provide an overview about multiphoton quantum technologies. Well, first, I would like to say that the goal of this community or this field is to develop applications that rely on multiphoton interference. And those applications, well, these applications can be for quantum information processing, for metrology, for imaging, for spectroscopy, and there are other possible applications. And as I said in the beginning, the idea is that we prepare some multiphoton systems. We force them to interact or to interfere. Then we see the output, and we use that to improve the way in which we can process information, to measure small physical parameters, to actually boost the performance of techniques that have been around for multiple years, such as imaging. And then another popular technique is to use these multiphoton systems to probe matter. For example, here we have these light fields probing an atom. And what's the idea, or why do we want to use multiphoton interactions? So here I have this cartoon. We have three spheres that represent three photons, and they interact through different paths. So we have these different paths. So after this interaction, we can have these photons emerging in different order. For example, if we have red, green, and blue, then in the output, we can have red and blue, green, or we can have the vacuum, and then we can have other possible outcomes depending on the interaction. Just to give you an idea, if we have, let's say, 3 photons, but if we have, let's say, 5 paths, this system can have 30 different interactions. And then if we increase the number of particles, for example, to 6, and if we increase the paths, then we can have 7,000 interactions. So this field utilizes all these possible interactions to do things. For example, to extract information, to characterize a physical parameter, to process information. And there is a field known as quantum simulation that uses all these complex interactions, for example, to simulate Hamiltonians that cannot be easily simulated in supercomputers, for example. I will briefly describe that. What's the origin of this field? Even though this field is very popular now, so we can trace back this field to the 50s when Hamburg, Brown, and Twist performed this experiment with thermal light. So they wanted to measure the diameter of a star, and a star can be simulated with a source of thermal light or a natural source of light. What they did is they passed this light field through this beam splitter. They obtained two beams, and they used two detectors. So first they kept one detector fixed and they scanned the other detector. And what they found is that they were able to see interference, but it was a different kind of interference. It was a non-local interference. And it was then found that the coherence of this system was described by this coherence function, where we have one part, let's say this term, that depends on one of the detectors. Then we have another term that is describing the other detector. This is just the product. So this is, I mean, there's not anything very interesting about this product, but there is an additional term that shows or relates this detector with this other detector. So this additional term describes a form of non-trivial correlations between these two detectors, and it's actually showing interactions that can be related to two-photon interference. And that was very interesting, and still that's interesting that you can get these two-photon correlations from a natural source of light that is classical and not quantum. And this two-photon interference is sometimes related to entangled photons. And as you probably know, if you have two correlated particles like these two correlated twins, if they are entangled, they will show very strong correlations, such that if you hit one of them, now if they were happy, after you hit one of them, they will both be unhappy because they are strongly correlated. So we have something like that going on here. So that original experiment was very interesting, and scientists tried to explain what was the underlying physics behind that experiment, and that led to the birth of quantum optics. And probably we can start. Actually, this field started with these two papers by Roy Glover, where he quantized the optical field. And then he introduced some quantum states of light, such as single photons. This is a truly quantum state of light. And then we have other states that can be classically described, but they are also quantum states of light, such as coherent states. You can see this coherent state as a superposition of Fock states. The most popular source of coherent photons is a laser, but then we can also have statistical mixtures that we can use to describe, for example, thermal light or natural light, such as sunlight. Then we have other systems that can provide multiphoton states, and we can produce that using a nonlinear technique known as spontaneous parametric down conversion. Here, what we do, we have a nonlinear crystal that absorbs a pump photon and produces two photons that are strongly correlated, such as these two states. In general, this state is described as two-mode squeeze vacuum state, and it's called two-mode squeeze vacuum state because most of the time you have a vacuum state, like here. You have a correlated vacuum, but then if you hit this crystal very hard, you can have one photon here and one photon here, or two photons here and two photons here, and that's mathematically described by this state. So if you have an experiment and you can produce any of these states or something like that, then you have a system, multiphoton system, and then you can start exploring these quantum interference effects for multiple applications. So another thing that becomes very useful is how, photon number resolving detectors will allow you to characterize these multi-photon systems. Most of the time, people use click detectors, and these detectors produce a click. When you illuminate them with 1 photon, with 2 photons, with 3 photons, it doesn't matter the number of photons, you always get a click. So in practice, you don't know the number of photons that you detected, you just know that you detected something. But you can use photon number resolving detectors and say, well, now I have 1 photon or 2 photons or 3 photons or nothing. And so here I show like a trace from a photon number resolving detector. Here you have voltage and you have time. If you detect the vacuum, you have a flat line. If you detect 1 particle, you will measure something like this. If you have 2 photons, you will detect something like that. If you have 3 photons, you will keep getting more voltage. And that allows you to identify the number of particles. Another way in which you can characterize these systems is by using multi-photon correlation. So you can have an array of detectors like this. You can also do photon counting. You can count the number of events that you have within a coherence time and then build histograms like this. And more recently, people have been using machine learning to characterize light sources. So there are multiple ways in which you can characterize these systems. Okay, so if you have your system and then if you have your detectors, you can start exploring these interference effects. Probably the most popular way in which you can do it is through the famous Hongo-Mandel effect. Here you inject 2 indistinguishable particles. You use these 2 indistinguishable particles and inject them onto the input ports of a beam splitter. And then in the outcome, you will have different possibilities. You can have these 2 particles emerging through the upper port of the beam splitter, or you can have the 2 particles emerging through this other port, or you can have 1 particle going up and the other particle going down. If we apply the beam splitter transformation, we will see that we can have a state like that in the output. And this state that you see here is known as null state. In this case, we have an n equals 2 null state because we have 2 particles. And this state has been used for multiple applications in quantum sensing and quantum information processing. So the most popular technique or the straightforward application is for metrology. So the idea is that you inject these photons and then you sense a target element like that, and then use your multi-photon detection to provide information about this phase object. This was recently demonstrated using multi-photon systems that were created in this PPKTP crystal. Then these states were used to sense a phase, and then the transmitted states were characterized by transition edge sensor that gives you photon number resolving detection. And to see an advantage of multi-photon systems, we have this feature information that is telling us how well we can characterize this phase object. When you use only click detection, you can barely surpass the quantum limit that is indicated by this purple line. So your red signal is what you get when you use click detection. You can barely get a quantum enhancement. However, when you use photon number resolving detection, you can surpass this quantum limit. You can get the blue curve. And this is very great because this is just an interferometer, and that's the basic for multiple quantum applications. Now you can have a more complicated arrangement. For example, you can have multiple interferometers here. You can have multiple phase shifters. And now to describe the evolution of the state along this platform becomes really, really complicated. And that's for example, this circuit has been studied in the context of random walks. And here you can see that the system becomes really complicated. This standard deviation is telling us how complex the system is, or the output. And we can see that when we describe this circuit using classical optics, we get this red line. The step is given by different Mach-Zehnders interferometers. For example, this will be one step, another step, another step, and another step. So we see that the complexity does not increase with the number of steps in your circuit. But when you use multiphoton interference, you see that the standard deviation increases, and this is good for quantum information processing. So here we see the outcome of a random walk. We see that we can have, for example, this outcome that shows a higher standard deviation. We can see that we have these wings. Those wings will increase the variance of the system. But when you don't have enough steps, you see that you have something that looks Gaussian, something a little bit like this. So recently, people have been using these ideas to build quantum computers. And for example, we have this experiment that was performed by a Chinese university back in 2020, where they used 15 distinguishable modes, 100 interferometers, and 100 detectors. And they used this experiment to demonstrate boson sampling, which is like a more universal form of quantum random walks. Recently, people have been using like matter interactions to increase the complexity of multiphoton scattering and multiphoton interference. For example, here we have this photonic crystal that was used to trap photons, and these waveguides were used to control the interaction between these two atoms. Sorry, I said photons, this should be atoms. There are other schemes. For example, here we have this optical fiber that it's also used to trap light. My group has been using plasmonic fields also to control the interactions between wave packets and to change the statistics. All these schemes will allow to build this kind of quantum simulators, but in theory, we expect that the use of these additional like matter interactions will allow us to control these systems in a more sophisticated way. So recently, people have been using all these different forms of interference in multiphoton systems, for example, for imaging. In general, diffraction forbids or establishes a resolution limit on the imaging. For example, if we have an optical system and we have multiple sources, if they are very close, we will see we will identify them as a single spot. However, by using photon number solving detection and by identifying each of these interactions, we can increase the resolution from something that looks like this to something that looks like that. And these ideas have also been used, for example, to create photon number solving cameras. These are cameras in which you can measure the photon statistics at each individual pixel and use these photon statistics to identify the source that you have at that particular point. Well, with that, I think that I gave you a quick overview of the field, and well, thanks for your attention.
Thank you, Omar. I think we're just going to give a minute or so to people who have questions so that they can put it in the Q&A, and then we're going to hand over to Marcos. You can already start if you want to, Marcos.
Oh, okay. Thank you very much, Neely. And I want to thank Frontiers for this nice opportunity to talk about quantum technologies in general. So we are part of this special session on quantum technology, and we have been talking This is the second opportunity for talking about quantum technology subjects. And I was chosen to talk about this impact and perspectives of quantum technologies 2.0 in short and medium term. So as you're going to see, I will talk more about quantum computation because all my colleagues, they already talked about quantum communication, the other subjects. So I ask you to go and see the other talks that we had previously, and I think that we're gonna have another one after this one, which from today. Okay, so the first thing is, so what is this 2.0? We are in the middle of the second quantum revolution that joins quantum physics, computation, and information in what is called the quantum information science. So this joins application in quantum information, quantum computation, and in general information science. So we do have lots of things happening right now in terms of applications. So, but of course, this always started a long time ago. I will talk about that. So in this talk, what I want to talk about is in general in terms of quantum technology, but I will not have time to talk for you. So we're gonna cover just two points on quantum technology in general. So quantum technology covers quantum computing, quantum communication, post-quantum cryptography, and also quantum sensing. So if I do have time, I will talk very briefly about quantum sensing, but as we will see, all the technologies that come from developing quantum computing, quantum communication, and cryptography as well, they are in some sense used to quantum sensing as well. So, okay, so everything started back in the 80s, from the last century, where we had this meeting by Richard Feynman and some other physicists and computations scientists, where they wanted to understand whether if you could do better in terms of computation and processing of information, if you consider quantum, nature of the matter. So from that point on, we did have a lot of developments in terms of both algorithms and in terms also of very important developments that happen in terms of the understanding of computation, in terms of general in a general theory of computation for quantum coding of bits, which is called qubits, and also how to develop what is a universal quantum computer and how that could be used mostly for simulating the specific quantum matter. But of course, everybody knows what are the most important algorithms for that were developed during the 90s, which is the Peter Shor prime factor decomposition algorithm, and also the Grover search algorithm, which is related somehow to what you just saw with Omar in terms of quantum walks. But after, but we have to mention one thing which is quite important from the beginning of the 2000s, which was the involvement of big companies related to putting money into this kind of technology. So before that, this was just like people from the academic side thinking about how we can improve computation by using quantum resources. But from 2001, we do have lots of companies putting money, high technology companies putting money into that. So we had some change in this horizon of development. So as I mentioned, in terms of the evolution of the quantum computing architectures, we did have some very shy development at the beginning, where we do have 2 qubits and 7 qubits, 5 qubits, and so on. But all of those related to different technologies related to NMR, technologies, which is good for a simulation of quantum features, but none of those, they were really solid platforms for quantum computing. The other one, which I should mention, which is solid because it has evolved somehow, is the trapped ion systems, and this has evolved quite a lot. I will talk about that later on. So another platform that appeared in the 2000s, it is a dedicated quantum computer, which means that this is an analogic quantum computer that just does a specific problem, which is the quantum annealing. But none of those are from D-wave quantum systems. They are universal quantum computers. So we want universal quantum computer, which works similarly to what the computer you have at your hand, and which you can adapt depending on the task you want to solve in your computer. And so you can adapt it in terms of algorithm and a code just to do whatever you want with your quantum computer. So as I mentioned, with the involvement of Google, IBM, and also Rigetti and other companies, big tech companies, we had the evolution of those platforms. This is mostly due to the development in terms of superconducting qubits, and also we had some improvement in the last years in terms of trapped ions, and as was mentioned by Omar, we also had this optical quantum computer by the Chinese government. So, but what is the interesting? Why those companies, they actually did get involved with this quantum technology stuff and this quantum computing? So this is not just because they were interested in academic problems. We do have some problems that in principle can be solved more efficiently if you have some computer, even a quantum computer, even if this quantum computer is not that efficient in terms of noise, noise avoiding. So it doesn't avoid noise, but even with that noise, some noise which is, it's present in this unperfect systems, we can do better things than the ones that we can do with classical computers. So of course, the first application which was thought that the quantum computer was good for was to simulation. So if you increase the time of your simulation and we want actually to treat real systems that you have presently, which are interesting for technology in general, you have to deal with macroscopic systems. So if you want to do a simulation on that, you quite fastly saturate all the power of any classical computer that you have due to the increase of the space, the parameter space, and the dimension of the variables that you have at hand. But if you use a quantum computer, the dimension is encoded in the Hilbert space. Therefore, the Hilbert space dimension increases exponentially. So this is a good place for doing computation, a natural place for doing computation when you want to simulate quantum features. So this was the general idea at the beginning when people thought about quantum simulation, and is, for me at least, is the most promising thing that you can do with a quantum computer. But this is not the only thing. Of course, if you can do that quantum simulation, you can also do important things in terms of technology that are related, for example, to quantum chemistry. You can actually, for example, you can simulate many biomolecules. You can simulate how drugs affect some other molecules and so on. So it's quite important in terms of chemistry applications. But there are also some gains in terms of biology, because you can move on in terms of those biomolecules and see what you can do to improve, for example, arrangements of molecules that have some organic or biological relevance. Then we cover another area which is quite important and in general computing, which is related to machine learning and optimization. So it is promised that if you have a near-term quantum computer, meaning that it has noise, it's not perfect quantum computer, you can also use some ansatz and some algorithms that allow you to do better than what you can do in terms of classical optimization. So this is important for many subjects. So I think this is the main reason behind all this technological involvement with those big shot companies. So for example, for bioinformatics, for finance and protein folding, and also from route planning, there are many applications that are used in the industry that can be, implemented if you have a quantum computer that can do a better solution for your optimization problem than any other classical computer. So this has evolved quite a lot recently, and this is one of the things that I'm myself related recently. So this is in terms of optimization and also in terms of quantum machine learning. We will see what they are in specific terms in short. So there are quite a few players that appeared afterwards, after the involvement of those big companies. So we have here Microsoft, IBM, and Google, as I mentioned before, but we also have many other companies or startups that appear due to this involvement. So some of those, they are related to software applications, to cloud computing, to systems and firmware and quantum hardware, and many others, and so on. So this is quite important because we saw an involvement of the academic side with those companies developing new startups that are talking right now about quantum, many subjects, many things about quantum technology. Okay, so the global investment has changed during this time. So for example, if we talk about 2015 in terms of million of euros, we see that, for example, United States, applied something around 360 millions of euros, while Canada was applied somehow some 100 million of euros, and so on. But if we see a new picture of that, so a newer at least, from 2021, we see that there was a huge increase of the money put into those technologies. So we see, for example, this is just the state money, just the money coming from state that was put directly into this technologies. So, for example, USA invested around 1.1 billion of dollars this time, and while Canada applied the same amount. We see some things, for example, which are quite interesting. So, for example, China is expected that it has, they have put something around 10 billion euros, something expected around 10 billion and 15 billion euros they have applying to this kind of technology. So therefore, this is why we see during the recent years, we see a huge development in terms of superconducting optical and ionic systems for quantum technology in general. So this is quite important. So state money put directly into the research is quite important for this development that they have. So Anyway, I like this map because this shows, this is from IBM. This shows the maturity horizons and tangible, tangible values for the potential advantage of quantum computers in general. So here I have two, let me show it for you better. So we have in blue, we have the a different industry. So we have the chemical and petroleum industries. In green, we have this distribution and logistics industries. In red, we have financial service, healthcare, and life science, and so on, manufacturing. So, and here we split, they split in this map in terms of chemical simulation, scenario simulation, optimization, and also artificial intelligence and machine learning. So the first horizon is something that will appear in the next few years. So meaning that this is the, more something that really is in development. So we see many things which are quite important that appear in the, let's say, 5 years, it will appear. So one of those applications which are quite important and can be, has a big promising to being more efficient in quantum computers is like vehicle routing, network optimization, and also transaction settlement, portfolio management. So the industry, not really the industry, but the financial market has a lot of interest in also in those quantum algorithms, because they think that perhaps we can, get some more, more money back out of those problems that when we optimize, the portfolio of the investments. Also, we have some nice development in terms of drug discovery and so on. But if we move on beyond 5 years, this is the horizon 1, horizon 2, which means that after some stable but not optimally working quantum computers, we might have some very nice, applications as well, which will be, which are promised to happen. And if you go beyond 15 years, and this is, like this is from 2019, so quite probably this map is not updated. But let's suppose that this is correct. So beyond 15 years, we have all others applications that could be, quite relevant for in terms of the development of the industries. So talking about 2 points which are quite important here. One is related to machine learning. So what is supervised machine learning, and for us to understand how this will change when we put some quantum ingredient into it. So supervised learning is just an automaton that can, split the information that you get. So let's suppose that I feed it with information about a cat and a dog, and then after many, many runs of this, I can, at the end of the day, have an automaton that can split in terms of 2 kinds of information. Some points, they are classified as cats, and the other points are classified as dogs. Okay, so this is automaton that can, so this is machine learning in general. Machine learning can only do a classification algorithm. So, but the problem for this, of this approach is that computationally it is quite expensive, because the machine has to spend quite a lot of time in terms of data feeding and in terms of what we call the learning curve. Okay, so this is quite expensive. But if we use quantum machine learning, we can actually use a sort of parallel processing that quantum systems allow us in a way to do this in a very short time. So if you compare the time for processing of the general classical machine learning, and you compare to what is promising quantum machine learning, we have a very nice future to look upon. Here, for example, there is an application which was shown a few years ago. How is the learning curve of quantum quantum machine learning compared to the classical machine learning? So, in terms of as the time of the data set increases, so we have a shorter time for the learning if you use a quantum computer. Okay, the other one is related to optimization, and there is a very important problem in optimization, which is related to all the problems that we can use in industry, which is the traveler salesman problem. So this is a very important in computation. So let's suppose that we have 4 cities here that are connected by all those roads, and we want to find the shortest route between all those cities. And let's suppose that you start at one point, one city, and then you go to the other cities and want to go back to at home. So this is a very famous problem in computation, but it's really hard to solve if you have too many cities, like in a real situation, and have too many routes. But there are many proposals right now that show you how can you solve this problem if you use a quantum computer. So there are answers which are that can use you can actually map this into a quantum system, which is called the Eisen Hamiltonian, and then afterwards you just get the fundamental state, the ground state of the system, and automatically you optimize the problem. So there are many answers. I'm not going to talk about that, just to show you how interesting this subject is. You can extend this if you go, for example, for optimizing traffic. So we have here some condensed traffic between 2 points in a city, but if you optimize it, you can actually distribute it around the city. So this is one possible application that, in principle, if you use a quantum computer to distribute among those many routes, you can get a better time for optimization against what you get in a classical computer. Okay, so we just talked about the important things that you get in terms of quantum computing and these algorithms that appear that the industry is interested in general. But there is something else which is quite important for this development in general, because this is the quantum sensing. So quantum sensing is using quantum system to detect things in general that you can if you improve the availability of your system in terms of measurement and detection in general, you improve the efficiency for sensing things like temperature, orientation, electric field sensing, fluctuating magnetic field, and static magnetic field in general. So just showing one system, but all the technologies that are somehow involved with quantum computing, and also for in general for quantum metrology, they are also related to some task in quantum sensing in general. So this is quite important, and this, I think, is one of the most developed areas in terms of quantum technology that promises a lot in the near future. So just for us to close on our talk, I'll just show you the trends, the Google trends for quantum sensing. So we see that in a 5 years scale, we had an average which goes around like 25 hits in the internet, but then after February from 2022, we saw an increase. So showing us that right now is the exact time to be working on quantum sensing, because there are many things to be discovered and used. So we can actually, if we discover a sensing like a GPS, for example, that somehow senses our positioning, and using quantum technologies, this is better than any other classical way to detect this positioning. So we can get better sensing with a better efficiency. So with that, I thank you very much. And if you have any questions or you want to check my website to see what we do, please access this link. Thank you.
Thank you, Marcos. And as long as people are thinking about questions to ask, I actually have a question for both of you. So what recommendations and guidance would you give to a student aspiring to pursue research in quantum technologies? And what would be the ideal starting point from your perspective?
Can I answer that? Yeah. Okay, so this is quite interesting because we have nowadays we have two different people, interested in quantum technologies. One is the academic in general. So we have our students, like I started talking about quantum computer more than 25 years ago. But right now, the layman is interested in quantum computing as well, because they are, hearing news about what quantum computer can do, what quantum technologies can do better than the general system. So we are starting here at Unicamp a different approach. We are trying to use less mathematics in general and letting people know what is, the quantum technologies and computation in general, in a general way. So I think it's quite a good opportunity as well for education in general, for public education in general. So I think that this it's interesting to, for the students in general, first to get in touch with a specific technology. Unless you don't get with a specific technology, you go to the lab or you have contact with experimentalists, you don't know how the specific quantum system works, and you don't. And secondly, you have to somehow simplify the way that you talk about quantum systems for people, for the layman. So that's my general point of view.
Yeah. One of the nice things about this field in general, quantum technologies or quantum computing, is that you can approach it from many different paths. For example, you can be an expert in condensed matter, and there's a path that you can follow to reach it. If you're an expert in optics, there is another path that you can take it. If you are an expert on math or computer science, then there's also a path in which you can end up working on this field and contributing to it. So I think that this makes the whole field very unique, because if you compare this with the industry in electronics, I mean, that made a huge impact in like a world impact, I will say, but you had to be an expert on one particular field. Now this field is so broad that you can approach it from many different paths. And that's, in my opinion, that's very nice. And also that's contributing to the development of the field, just because you have people from many different fields. As Marcos described, now this field is progressing so rapidly, and I think that it will continue like that. Yeah.
Okay. Marcus, would you be able to stop sharing?
Oh, yes.
Thank you. Just a second. I'm going to start sharing again. Okay. All right, thank you so much. So I think we're going to wrap up now. And I want to thank again all our speakers, Omar and Marcos. Thank you so much for joining us for this webinar and for making this possible. And if anyone would like to get in touch with us, or if you still have questions for our speakers, feel free to email us. You see our email displayed here. And if you have any questions about leading a research topic or about our journal, we also have our contact information here, and we'd love to hear from you. So I wish everyone a good afternoon, and thank you for joining us here today.
Thank you very much.